estimate is the advantage of impossible differential attacks. The talk will be given by Celine Brown.
Okay, so hello everyone. So I'm not Celine. Celine was not able to be here, so I will try to present her results in the best possible way. So just try to figure out how it works. Okay, so this work is about impossible differential cryptanalysis, and more particular, in analysis it gives a more accurate estimate of what we call the advantage of an attack. So the advantage can be seen as the number of qubits that is won during the key sieving phase, and correctly estimating this quantity is very important because this has a direct impact on the time complexity of the key recovery attack. So this talk will be divided into three parts. So first, there will be an introduction, like explaining what is it, recall what is an impossible differential attack, and introducing the advantage. So in this talk, impossible differential attacks are seen as statistical attacks. So I will show the modeling that was used before, the binomial distribution to estimate the advantage, and show why this is actually it's not the best possible estimate, and then show a better way to do this. So the second part will talk about how to approximate the advantage using multivariate distributions, and then impact and some experiments on key recovery attacks will be given. So impossible differential cryptanalysis is a very important family of attacks against block ciphers that were introduced independently by Rasmussen and by Bianchi-Shamir in the 90s. And so if you're given a target cipher, you can divide it into three parts. So you have some first rounds, then you have some last rounds, and we're interested in the middle rounds that are E prime. And we will say that a differential delta x delta y over E prime is impossible if accuracy probability is 0. That means that there is no key that can encrypt a pair of inputs with input difference delta x to a pair of outputs with output difference delta y. So usually when a block cipher is given, it is always possible to find like such differentials, and this gives a distinguisher for some rounds. And then this distinguisher can lead to a key recovery attack if we extend this distinguisher some rounds possibly to both directions. So typically, a key recovery attack is composed of three phases. So the first phase is the data generation. So the attacker will try to generate pairs from a set of plaintexts. The second part is the key sieving phase. So that means that attacker will try different keys, and all these keys that make the impossible differential actually possible will be discarded. So this gives us a sieving of the key space. And finally, the last part is the exhaustive key search. In this part, we will search, do an exhaustive search for all keys that were not discarded during the previous phase. So the time complexity of an impossible differential attack depends on all these three phases, and is typically taken as the maximum of the time complexity of the individual phases. So there have been some more or less recent publications that analyze the complexity of these attacks. In particular, so the previous works were focused on the first phase, the data generation, and the key sieving phase. And it has to be noted that the data complexity also plays an important role because it influences actually the time complexity of these phases. So this work is more focused on the last phase, so the exhaustive key search. So the exhaustive key search, its time also depends actually on the advantage that we can get from the data we have. So it is very important to do an analysis on the link of the data complexity and actually the exhaustive the advantage because this will give the complexity for the exhaustive key search. Okay, so I'm going to try to recall some notations. Just to say that when more than one structure is used for the attack, the data complexity for the distinguisher and the key recovery attack is basically the same. So we will now focus on the distinguishing part. So the notations are as follows. So here what you see is the middle cipher, like the middle part E prime. So that's the one that is covered by the impossible differential. So we have two, so it's truncated differential, we have two spaces, the delta x and delta y. So in this work they are seen as linear or affine spaces. And so an important notation is the quantity L. This is the number of bits that have between 0 in the output. And by the notation like, I'm sorry. Okay, I don't know how it works. Anyway, probably yes here. So this will symbolize the number of elements that we have in the set. So it's as the number, the block size is n, we have inside to the n minus l elements. So another important element is the structure, what we call structure. So this can be seen just a subset of 2 to the t elements in delta x. And we're actually, for each structure, we can just fix this part here. If we have 2 to the s structures, and inside each structure we have 2 to the t elements, for a data complexity 2 to the s plus t, we can generate 2 to the s plus t, like the quantity that we see here, number of pairs. Okay. Yes, so something that also Felix is wanting to say is that here the number of elements actually, it can be, sometimes it can be also be smaller than the number of total elements in delta x. Okay, so here, as I said, the impossible differential attacks will be seen as statistical attacks. And that means that statistical modeling similar to classical differential attacks can be applied. So statistically, a pair will be seen as a sample. And we have a random variable t, and t equals to e will represent the event that the differential appears exactly I times. So in the case of impossible differential attacks, the only event that is of interest to us is t equals to 0, because we want that because the differential is impossible. So in the seminal work of Knudsen, this variable was modeled to follow the binomial distribution with parameters ns. So probably I forgot to say that ns, so it will be symbolize the number of pairs that we need for the attack, and probability p, that is 2 to the minus l, and l is, just to recall, the number of bits in the output difference that have to be, like the difference has to be 0. So by here, the b here will stretch out that this random variable follows a binomial distribution, so we can compute this probability like this. So we get this accurate approximation, and this gives the first term of the Poisson approximation. So the advantage of a key recovery attack is exactly so as I said in the beginning, the number of 1 key bits during the key saving phase. So for example, if your key is 4 bits long, and during the key, example, and during the key saving phase you manage to discard out 8 keys, so half of them, that means that the advantage will be 2 bits. Okay, and the false alarm error probability, this is given by all the random permutations that never verify the differential, even after all the pairs have been tried. So the advantage of distinguishing attack is exactly defined, so it's linked with the false error probability, and is defined as the log 2 of this false alarm. Well, we have also a minus somewhere. Okay, so If I said so if as in the previous slide, the pass probability is we suppose that it follows the binomial distribution, and it's a Poisson approximation. Then the advantage estimate, we just can take the previous formula and apply it here. So we get that the advantage estimate is this quantity where NS is the number of pairs. Céline made a lot of experiments because she wanted to show that this approximation is not actually very accurate. So she did experiments on 12 different permutations. In particular, she used a PRNG to generate to the 26 random permutations. And for each of these permutations, she tried to see how many of them verify the impossible differential. So she did experiments with different data complexities. So S is linked to the number of structures, and so we have here different values for S and T. With A hat, we represent the experimental advantage. That's what she measured during the experiments. Here we have the classical advantage with a binomial distribution. So here our result would correspond to this. And the last column is what we'll introduce in the following slide. It's a new modeling using the multivariate hypergeometric distribution. So what you can see from here is that this is what we try to match, that the classical approach does not give close. It's quite close, but it's not that accurate. On the other side, with the new modeling, we have a perfect match. So this is just an introduction to the theory that was developed, and this theory actually includes to use to approximate the advantage by multivariate approximations. Okay, so we have one pair. So one pair satisfies an impossible differential. If actually this is equivalent to say that we have two messages that collide, so they have exactly the same value on the L bits. The L bits is on the output of the impossible differential. So for example, three messages give us 3 pairs, and one message gives us 0 pairs. So the first difference with the classical model is that here we don't, Céline does not consider pairs anymore, but single messages. That means that a sample will be a single message now, and not a pair anymore. So this is to count the number of pairs. So she defines a new algorithm for doing this. For this, we take a vector L. So this vector L is of L bits, and for each element, we will increment Li if the value actually we get out of the encryption is exactly I. So for this, the number of pairs can be computed by doing only sum, which means that if we have no pairs, that is the event that is interest of us, means that actually in this vector we have only 0 or 1s. So if we have multiple structures, this was for one structure, but we have multiple structures, then we have to do the sum of all the pairs that we get from each structure. So in the impossible differential context, false alarm are brought by the random permutations, for which, when using n messages, we're not able to find a pair fulfilling the truncated differential. And using the previously defined approach, so what I said, the problem of finding pairs is equivalent to the problem of finding collisions in the vector L, and this approach has actually a link with the approach that was developed previously by Céline and Kaisa for linear attacks, because indeed the number of computed pairs in the structure is linked to the computation of the chi-square for the multidimensional linear case. So for the moment, we will see what happens with just one single structure. So to estimate the advantage of any possible differential attacks, one analyzes the distribution of variable or random variable that is associated to a scoring function. And here, the scoring, so in this new approach, the scoring function will be this L. So L will be the random variable that we'll try to approximate. So we want to estimate the probability that no pairs fulfill a differential. That means that the vector L only has 0 or 1, so there are no collisions for the vector L. So we could do this if we assume that platex are repeated. This is possible to be done with the multinomial distribution. That is, this is a generalization of the binomial distribution. However, as Celine and Kaiser showed in the previous work, it's repetition. I mean, non-repetition actually is very important. So in this case, instead of using the multinomial distribution, they use, Celine uses, so the multivariate hypergeometric distribution. So both distributions are like, they can be seen as the event of having an urn with different balls for different colors. And what we're interested is to see the probability to see a certain repetition of the colors up to certain rows. However, the multinomial distribution supposes that we can put the balls inside the urn again, and the multivariate hypergeometric no. So this is why we use, Celine uses this one. So now if like the scoring function is modeled with the multivariate hypergeometric distribution, we can use the formula and compute the probability of the event that is interest of us, so no pairs, because it's an impossible differential attack, and so this is the formula that we get. So this was for one structure. Let's see what happens with multiple structures, because like a lot of attacks, an attacker would like to take advantage using multiple structures. So if we assume independence of the structures, then we can devise like the following estimates. I will not go into details, but the idea is that we take what happens for one structure and multiply this, and them, and then we take the result log 2. So this is like with the estimate with the multivariate hypergeometric distribution, and this is a classical one. So you see that now we have a difference. This is the difference, the new term that appears. And if L and N are actually close enough, so this can have a real impact. So in general, this independent assumption is accurate as long as S plus T, like 2 to the S plus T is smaller than 2 to the L. Well, this symbol means that it should be quite smaller, but on the same time not that much. So if this, so Celine did experiments, and so she saw that this independence assumption doesn't hold anymore if S plus T is strictly higher than L. But it starts to hold again if we are very close, the decomplexity is very close to the whole code book. So if you do not do this assumption, then the model is more complicated, and it's based on the B multivariate hypergeometric distribution. So this distribution is more complicated to manipulate for real block cycle parameters. So it is only used here to estimate the maximal advantage, as explained so in the next slide. So here in this slide we generalize the definition of the vector L that we've seen before, but in the case we have more than one structure. So one row is the L that we've seen before, and as we have to do the S structures, we have to do the S rows. So as we have inside each structure 2 to the T elements, we know that each row will sum up to 2 to the T. And as the encryption function is a permutation, we say that the sum of the column is smaller than 2 to the L minus T. The maximal advantage is got when the whole code book is used. So in the impossible differential context, this is a little bit different from the classical statistical attacks, because the successful probability in this case is 1, and the advantage increases as the data complexity increases. So we can prove the previous formula only in the case where the data complexity equals the codebook, and in this case we get the maximal advantage. And this is not the case when the binomial distribution is used and when we deal with pairs instead of plaintext. Okay, so let's go now to key recovery attack. So key recovery attack is not that different. So what actually happens is that we have here the possible distinguisher, and then we extend this to some round backwards and some round forwards, and we get an attack on like all this number of rounds. So I don't think I will need to explain other details on this. Just what I said also in the beginning, it's that when one structure, more than one structure is involved, the data complexity of distinguishing and a key recovery attack is the same. So Celine did experiments for like the key recovery phase, and for this she implemented a toy cipher. This is a 16-bit phase cipher with 4 branches. So she took an impossible differential distinguisher where the input difference and the output difference are both of 4 bits. And then she did 2 kinds of experiments. So the first one she extended 2 rounds before, 2 rounds after, and the second experiment 1 round before and 2 rounds after. So this is the result that she got. So as here we see, this is the experimental advantage. This is in green we have the advantage, like in this in the paper. So with the new theory, and the one this was what was the advantage one modeled by the binomial distribution. So, and of course, as you can see, so in both tables, this like the new theory gives very accurate results. Okay, so some other remarks concerning when we only have one differential. So we have only one differential. The parameter that we called t before is only equal to 1, and very often the number of pairs that is given by this is estimated. We do like a rough estimation, we approximate to the power of t minus 1 by 2 to the t. So in more cases this works well. However, when t is not equal to 1, this approximation is not good at all, because there's a big difference between the two values, and actually this has an impact on how people estimated the advantage. So Celine proved that for all actual approximations, the maximal advantage, she proved that it is 72, but this advantage was previously estimated as 142, and this is exactly because people did this approximation. So in the key recovery attack, it's not, the two values are, like, we don't see exactly the difference, but when we get to the distinguisher, it has played, the difference can play an important role. So in particular, we have a difference. So if the cipher that we're looking at, it's have words of 8 bits, actually the difference is not important because of the parameters, n minus l is not that close to n. But for 4-bit words, for block ciphers using 4-bit words, actually the two values are, this can have an impact. So this is why the time complexity of the recent possible differential attack on Simon is larger than actually was estimated, because the advantage was wrongly estimated. Celine looked at some previous attacks that were done on the L-block cipher and the crypto cipher. So both are impossible differential attacks, and for the first one the advantage was estimated to 30.6 bits, and with the new theory of Celine this is corrected to 28.69, and for crypto something similar happens. So we have the correct advantage as actually 3 bits lower of what was expected, which means that for these attacks the complexity of the exhaustive key search, so the last phase, is actually most important that was estimated in these papers. However, for these examples, this does not have an impact on the time complexity of the attack, because the last phase, the exhaustive key search, was not the dominant term anymore. However, such type of analysis is very important to show because if we have an attack that the last phase has like the most important complexity, then wrongly estimating the advantage can have a really important impact on we will underestimate actually the complexity of our attack. Okay, so to conclude, this was a talk about how to correctly estimate the advantage of impossible differential attacks, and in particular we have a new formula that can have an impact when L is close to N. And a final point that was not discussed during the talk is that typically in impossible differential attacks, one tries to do the attack by first choosing plaintext and then choosing ciphertext, and then looks which data complexity actually is lower, and so the data complexity is taken as the lower of these two measure quantities. However, what Celine shows is that if we use more than one structure, actually the two complexities will be exactly the same. We can do the attack by choosing plaintext or by choosing ciphertext. Okay, that's all. Thank you very much.
Thank you very much. Unfortunately, we are a bit behind the schedule. So if you have questions to send me, please.
It's better to send them to Celine by mail.
Please during the coffee break. So